Okay, so good evening. Um, so last time we looked at lists, and I promised we would continue with that, but I'm going to take a short detour first and talk a little bit about assignment 4. All right, so before that, I would want to show you the enhanced evaluation, expression evaluation code. Right, so I promised you that I would brush it up and I will upload a better version, and I just did that. And that's relevant to the assignment actually. So what I've done was, besides just brushing up the code, I have created a piece of code that draws the tree so that it's a lot obvious what's happening, right? And instead of reading expressions from the keyboard, I just added a bunch of tests, and you're of course invited to add more, right? Which will print the tree, evaluate it, right, whenever the expression is correct. So I'm going to run it very quickly. Right, there's quite a bunch of tests. All right, so it starts here. So you see all the expressions that are being tested. The incorrect ones are coming first, right? And you see that they're correctly detected as incorrect. And then as we start having correct expressions, you're going to see the tree being drawn and the evaluation, right? So now it's a lot clearer what happens with the expression, how it gets encoded inside, and so on. So you can go in and add your own tests and play with it and figure out what's going on. Some of the trees are huge, okay, and it's actually fun to play with. Now, why is this relevant for assignment 4? Because assignment 4 is about trees. And we're not looking specifically for expression trees, but we just want to look at general trees, which is nodes that have children, right? Have 2 children. Especially, we're looking at binary trees. And because we have such a handy method now for generating trees, because trees are typically difficult to generate from the input, we're going to use expression trees as examples of trees. But the methods that you have to implement, the functions that you have to implement, don't care whether it's an expression tree or any other kind of tree, right? It's a structure with nodes that are linked together. So this entire enhanced evaluator is absorbed inside assignment 4. And because of that, assignment 4 is a rather large file. So you don't have to be scared about that, because you don't have to understand all of it, right? So now the file has 3 sections. There's of which only one you need to change. So there's a first section that contains declarations that have to come first. You're not supposed to change it, but it's a good thing to understand this. And this is something you already know, as a matter of fact. Notice that I took advantage of the trick we learned last time. I made it into a type def, so it's easier to write these nodes. All right. Then section 2 contains solution templates, and this is the part where I have to add your solutions, right? And remember, these are talking about trees, not expression trees. So, for instance, we want to have to write a function that counts the number of nodes. Okay, so receives a tree. I don't care whether the nodes are operator nodes or operand nodes. We don't care about expression trees, but there's nodes, and we want to count how many there are, right? So you have to fill in your code. Feel free to change this. I made each function return some value that allows the code to be compiled and run. Now, so this is exercise 1. right? And this is your template. And it's clearly written here that you need to write your function only between this and this. Okay? Now, for convenience, you are provided with a test function, right? So this will run and will pass in expressions to, trees. So here we build a tree. It happens to be an expression tree, but we don't care about that, right? So we're taking advantage of all the code that we've seen in enhanced evaluation to produce a tree. And then you have to, I'm calling your function, the one that you're supposed to write, to produce a result for T1. And you see here what I'm expecting, and here I'm going to print your result, and they should match if you write a correct result, right? So you have a bunch of tests for your convenience, and these tests will tell you how correct your result is. And then you move on to exercise 2, which requires you to count the nodes on a specific level. Now, if you're wondering what that is, it should be relatively simple, right? So this is a level. This is specifically level 2 in the tree, right? This is level 1. This is level 2. This is level 3, right? On level 3, we have 4 nodes. Is that clear? Yeah. And then if I go here, for instance, this is level 1, 2, 3, 1, 2, 3, 4. So on level 4, we also have 4 nodes. Okay, so depending on the configuration of the tree, the number of nodes may vary. Right? And so on. Okay, so let's go through all the questions and clarify them. Right, same thing, right? So you have a bunch of tests, and you're given the expected result, and you can compare against yours, right? Your function is called here. So obviously this part you don't need to modify, right? If you write correctly this part, which is where your solution should go, then everything should run properly and tell you whether you're doing a good job or not. Exercise 3, count leaves. Leaves are nodes. They do not have descendants, meaning that both children are null, right? So if we go here, these all are leaves, right? Here, things are a bit more complicated, right? So all the numbers are leaves, it so happens, right? But your test for leaves should not be whether it's a number or not. It should be whether both left and right are null. That would tell you that it's a... So you need to count the leaves in the tree. And again, the tree can be very jagged, so you have to find a way to count. And then exercise 4 checks whether the tree is balanced, right? So a balanced tree looks like this, right? Meaning that for every node, the left subtree and the right subtree have the same depth. Okay, and when I say the same depth, we need to define the depth. So the depth is, let's talk about the depth of a node. So if I take this node, its depth is 2, right? Is the distance from that node to the root in number of hops, number of edges. So the depth of the tree is the longest path in the tree. Any node I can take from this tree, right? And I find the one with the longest path to the root, the deepest node, and that's the depth of the entire tree. Now, for each tree that is not empty, we would have subtrees. So this would be the left subtree, this would be the right subtree. And each of the subtrees has their own depth. I can think of this being the root and calculate the depth. And then for a tree to be balanced, the depth of the left subtree and the right subtree are the same. But then recursively, inside each subtree, the depth of the left subtree and the right subtree are the same, right? So it's a recursive property. So looking just at the root is not enough. Obviously, this is not balanced, right? This is not balanced. This is not balanced. I think most other trees. This one is balanced, right? So you have to check whether the depth is the same, and then recursively whether for each tree is balanced. Each subtree is balanced. Okay. So that's another question, same pattern. Then you have a test. All right. And then there's an exercise that is asking you to check whether a node is contained in the tree. So you get a value, and we're looking only at integers. So here we can specifically take advantage of the fact that we have expression trees and look only for nodes that are integers, right, and check whether the specified value is inside the tree or not. Each of the questions will probably take less than 10 lines of code to write. Be aware of that. Don't write. If you're writing more than 10 lines of code, you're probably not doing something right. Now, as you run this code, right? So if I go and sorry, not here. If I go and run this code, right, I'm going to get exactly, a pretty much similar output, right? But you see that it's the result of all tests, right? So for instance, this is the result of the last test for contains, right? So we're saying contains 2. 2 is inside the tree, right? It has several occurrences actually. And then we're expecting 1, and I got the current result, which is the default value that I'm putting there, which is 0, right? So once you fill in that function, this result will be correct. Now this output is very long. So this is the test for contains. So here we start the test for contains. Before that is the test for is balanced, right? So you see here is balanced, right? And we have 8 tests for is balanced. Then before that, we're going to have counting leaves. Okay? So this output tends to be very long. Now, to avoid this in your development, because if you run the code and you have to see this output every time, it's going to be quite painful, right? So my recommendation is to go right at the end in main, and you see you have 5 tests. Each 5 test sets contains 8 individual tests. So when you work on count nodes, go ahead and comment these out. Right? You finish count nodes, test out, comment out test count nodes, uncomment the next one, right? So then your output is a bit smaller and focused on what you're currently doing. Right? You finish this one, go and comment this one out and uncomment this one. And so on and so forth. Okay? That clear? Cool. At the end, of course, what you want to submit is a file that has all the tests uncommented. Okay? So remember to uncomment all of them at the end. Cool. Any questions? So it's going to be a bit difficult to navigate, but in terms of how much you need to comprehend out of this and how much you need to implement, it's actually quite reasonable, so don't be scared. Cool? Cool. Back to lists. So let's see, where were we? So we've done a few list primitives, right? Quite important ones. So we created an empty list, right? We had the ability to append elements. We had the ability to delete the first element. All right, and that's pretty much where we left it off. So let's see if we can delete the last element, for instance. Or no, let's start with appending. Let's not be destructive. We delete later. So we want to prepend an element. All right, so how do we do this? As we did before, we have to create an element, right? And creating, an element starts with allocating space for that element. All right, and data equals element, and we might be inserting into an empty list, right? So in preparing for that contingency and also for being defensive, let's set the next equals null. Okay, so now we will have two situations. Again, the list is empty or it's not. If it is empty, then this element is the only element in the list. Okay, so whatever we're doing for append, it's exactly the same thing we should do for prepend. Right, so L start equals L and equals n is assigned n, and L is 1, and we're done, right? Notice that we have already set the next to null, and this is precisely what we need to be doing in this case. Else, okay, so this becomes the first element in the list. So n next should be equal to L start, right? So the next element of n, since the n becomes the first element of the list, the next element of n should be the current first element, right? And then L start should be assigned what? What do you mean by the next? So I'm prepending. Which one should be the start of the list? Okay, let's think of it in the following terms. So we have lockers, right? We're working with lockers. We're at the train station where the left baggage is, where you can leave baggage in a locker and you get the key, right? So I'm going to have a locker that contains two little boxes. On one I write start, on the other I write end. Okay? And then right? My list is going to be, the start contains the key to the first locker, which is the first element of the list. Inside that, I put the key to the second. Inside the second, I put the key to the third. All right? And at some point, I'm going to have the last element of the list, which contains no key. In the original locker where I keep my list, there's a box, a little box called end inside, right? A little ball, right? A little ball containing, the keys to start and end. So there's an end, and that contains, there I have a copy of the key to the end element, right? Okay, maybe we have a good, well, we have a better one. Good marker. So I have a list, right? The list is a locker that contains 3 elements, 2 keys, start and count, right? The start points to the first node. So here I have a number, let's say 0, and point to the next, which is another number 1, point to the next. 2, and this one has no key, right? So I have a key from here to here. I also have a key from the end to this guy, right? This is what my list, how my list is encoded. Now I want to print 10. So I want to say that this element that contains 10 maybe becomes the first element in the list, right? So if I wanted to become the first element in the list, obviously I have to make this guy pointing here, right? The question is, this, which is L dot star, where does it need to point? To N, right? Very good. So I have to go here. And then we have prepended. And we have prepended. Anything else we need to do? Yes. So L count length plus plus. So notice how we have decided on an encoding for the list, right? And as long as we're consistent about it, we get essentially a list, right? And if we are in Python, right, the fact that we say square bracket 1, 2, 3, 4 separated by commas and close the square bracket, right, that will be encoded in exactly this, what we have here, right? We have this structure representing the list, and then the chain of nodes that hold all the elements, right? And as long as we have decided on this encoding and we are consistent in all the operations, we have essentially a list, right? So the list is very much in the eye of the beholder, right? As it is an integer represented by 32 bits, that the value of integer, it's a string of 32 bits. The value, the integer value represented by those 32 or maybe 64 bits, that's in the eye of the beholder. That's in your mind. That's an encoding. As long as you are consistent with it, as long as any time at any point when you look at 64 bits, you know how to convert those into a number, you're going to be okay, right? As long as you're going to look at these structures and you're going to see a sequence of integers, you're going to be okay, right? The world makes sense. But it's actually nothing inside here screams at your list, right? It becomes a learned trait. Okay, so in the good spirit of what we've done so far, let's test it. So what are we going to do? We're going to, instead of appending, let's prepend. Okay, and when we prepend, we're going to insert the elements in reverse order, right? Um, so perhaps it's good to, right? So notice how stuff is prepended, right? 1 goes at the front, then 2 goes at the front, and so on up to 9, right? And then what we do is we keep deleting elements from where were we deleting? From the delete first, right? So we are deleting them from the front, so you see the list decreasing, and by removing the first element. All right. So since we are prepending now, we should also have a function that deletes the last, right? So let's do that too. All right. So we can delete from the empty list again. So we're going to copy this. All right. So also we want to return the element that we are deleting, right? So that's a very typical thing. To be defensive, right? So you're going to say, oh, we're never going to have a length less than equal to 0, but maybe we have a bug in our program and somehow, right? So what happens? Then length is negative, and I would be attempting to perform some operations from a list that is completely inconsistent. So it doesn't make any sense. Yeah. Yeah, you could. So if you want to be really defensive, you should say or L next, L start equals null, right? Or Ln. And then you should augment this, attempt to delete from empty or inconsistent list, right? And again, everything we're doing says that this will not happen simultaneously, right? So if this is greater than 0, then L.start will not be null. But again, might have a bug, right? So, and it's especially true, now it's simple, we can see bugs relatively easily, we can correct them easily, but later you're going to say, oh, lists are finished, and let me build something on top of lists. Let me build two-dimensional matrices, right? Which would be lists of lists. And then I create an entire scaffolding for matrices where I'm assuming that lists are a basic block from this point on, right? So I'm going to regard all this code as, oh, from this point on, this is part of the language. This is predefined. This is like it was an instruction or instruction is defined inside the language, right? And I'm going to treat them as sacred, sort of blessed, sacred, right? But it turns out that they're still subjected to bugs, and I'm going to use them in such ways that you never know how they at least may become inconsistent. So at that point, this kind of condition may save you, right? And you're going to at that point you're going to say, oh, I have no idea where this is coming from, right? Why this might be happening. You've completely forgotten about the code, how this works. At that point, even you, the person who coded it, will only remember this. And that's because this is the intention of this API. We want to be concerned with what we can do with this and now not how we do it. Okay? We want to know how to drive a car, but not how the car runs. So it's the same thing. At some point, we're going to forget. And then this kind of statements are going to save us at that point. So now, the thing is, can we easily delete the last? What do we need to do to delete the last? Because it's very easy to delete the first. We need to go to the second last. How do we get to the second last? Right? So we have to traverse the entire list. That may be a potentially costly operation, but we have no choice. So, node equals L start. And let's write a for loop. Second not equals to L and second last next, right? And then second last is assigned second last. So when we finish this loop, and notice that there's no body to this loop, when we finish this loop, second last will be the second last element, right? Why is that? Because this, whenever we finish the loop, this is true, this is false. Right? Whenever we finish the loop, this is false. Do we agree on that? So let's reason mathematically. Whenever we finish the loop, this is false. Which means that if I put here equals equals, that is true. Right? Which means that the next of the second last is the end. So it has to be the second last. Okay? So now, since we have the second last, what do we do? Well, we have to say int result equals L last. What did we call it? Value or data? All right. And then what do we need to do? Next. You mean this one? Good question. What did we call it? N. Good. Very good. Thank you. So then what do we do? Second last. Very good. Somebody said free. What do we free? Right, this is last element. Finally, what do we need to do? Not yet. Well, we need to do that as well. So length minus, but there's something else we need to do. And yeah, I would do it first, but it doesn't matter about the order. null, right? And yes, we want to return something. Okay. So, question: what if I put this above? Would this work? No, right? Because we will be freeing this. This is already null, right? So we'll try to free null, which will bomb, right? So at that point, we would be doing we're making two mistakes: trying to free something that was not allocated, right? But also at this point, we have lost the allocated last element, which means that we have lost that piece of memory. We have produced a memory leak, right? That memory can never be found and returned to the system, not for as long as the program is still running, right? But remember, programs that run for a very long time are not uncommon. So for instance, this Sublime that you're seeing, this editor has been running for since the beginning of the semester. So I have not stopped it since, so it was all your Python files. I have closed those, and now I have started to open the C files. And since then, I have not closed it. I have not rebooted the system. Okay. So then, if this editor is leaking memory, would be leaking memory, right? All that memory would be slowly accumulated, which is something I should actually check. I should see what's the memory usage of Sublime. But we did look at the memory profile, and we didn't see anything unusual, right? So let's now try this. Let's test this, and we do that by doing delete last. And we're getting a segmentation fault. So let's see what worked, because something did work. All right, so it didn't work when we were about when we removed the last element. Okay, so the removal of the last element didn't work. Okay, so we have, as we did here, I think, right? We had a special case, right? So what if we have a single element in the list? Let's see what happens then, right? So at that point, this won't work well, right? Because second last arrow next is going to be null, right? Ln is going to be the current element. So this is not equal, right? This is true. And then we're going to try to do this, which means that second last becomes null. And next time when we try to do second last arrow next, that's going to bomb, right? So that's how this is going to bomb. So let's distinguish between two cases, right? So if L length is greater than 2, then we can do exactly what we have done, right? Else, what do? All we have to do is remove the only element and return its value, right? So int result, let's just make sure that we collect this value. So is L start data. All right, we don't need to go anywhere. Then we have to free and then we have to say L start equals L and equals null and return result. Okay, and we could make the code a little bit nicer by saying int result here, and then we can set the result here. We can also set the result here. And actually L start data and L end data are the same thing here. I could say end data, right? Then these two expressions look the same, and because they look the same, I could say result equals L and date, right? And then I don't need this here anymore. 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 And at the end, all I need to do is return result. Okay? Now again, free L start is as good as free L end. All right, and well, we can't do it here. So let's try and factorize from here, but it can be done. All right, so now it's actually greater than equal to 1. Doesn't need to be 2. Yes, sir? And reduce the length as well. And the length will be reduced no matter what, right? So we can reduce the length right here. Very good. Okay, great. We're deleting two elements at the end? Seems so. Why? Right, so 1 is 0. 0 is here, right? And I do exit 1, so if I have made it here, the list is not length 0, right? So otherwise, if L.length is greater than 1, which means at least 2 elements, we find the second last. And this case seems to be working fine, right? Because we see how we are correctly removing the last until we get to the end of the last element. I need to put what? That's very true. Absolutely. Very good. And correct. Okay. So, is this okay? Line 81. Yes. Why would you not put it there? What do you mean, give any variable anyway? We're not in Python again. So everything I have allocated with malloc, I have to free before I stop using it. All right? So C does not have a garbage collector. So everything that has ever been Emma-locked has to be freed before stopping to use it. Otherwise, nobody else can use it. Okay? It's as if, you know, if I free the content, or if I don't use a locker anymore, but I have not returned the key to the management, then nobody can reuse that box, right? That locker box. Yeah, cool. All right, let's append two lists, because this is one of the fun things to do. So before we go there, and that's going to be connected to the next homework, right? This is a relatively expensive operation, right? Generally, what we want is all these operations to take constant time. Not sure whether that you understand what that means, but whenever we have loops, that's not constant time, right? The loops can execute a variable number of times. Typically, that number of times is proportional with the input, right? And they result in linear time. Sometimes you can have loops inside loops, and then typically the time is quadratic, right? Now, sometimes you're able to increase your counter in the loop, not by one, but in a smarter way. Let's say you double it over time, right? So then that loop is logarithmic, right? If you increase it, if your step is not constant, but it's variable, say it's doubling, then you're going to get a logarithmic number of times, right? And you can have nested logarithmic loops, so then you get log square. But most typically, you're going to have one linear loop and one logarithmic loop, so you have something like n log n. So n log n algorithms are very common, right? The important thing is that whenever we have operations on a data structure, we are chasing constant time, right? Why? Because you see, we have another loop in main, right? We have for, and then we have a while here, right? So each of these loops add their own linearity, non-constantness, right? So then if we are deleting last, and this is non-linear, the non-linearity of this guy combined with the non-linearity of this guy is going to lead to a quadratic operation, right? Now, when we have 10 elements, you can't see the difference. But when you have billions of elements, you will definitely see the difference between 1 billion elements and 1 billion square. 1 billion operations and 1 billion square. Now, one interesting thing that we could do to make this operation linear, and not just this one, but a lot of other ones, is to create a cycle. Okay? So our encoding has this chain of elements, and instead of the last element having null, which is redundant information, because I already know that this is the last element, because m points to this, right? I could send this here. Okay? Or maybe, wait, actually this will not work. This will not work for delete, but it will make some operations, right? So one thing will be create a cycle, right? And then we get what we call a circular index. The other thing that we might do is to create an extra link. So here, from this point on, we have two links, right? So this points back, and we have a chain going back. And this will be a doubly linked list, right? So I have a set of arrows pointing forward, and then inside every element, I have a backward link the chain of backward links goes through the links in the backward direction, right? So that will make insertions and deletions much easier in the list. So finding the element that is before the last element would be a lot easier. Okay? So in the next homework, we're going to try to play a little bit with these, an extra layer of pointers so that we make some of these operations a bit more efficient. Okay? So let's append two lists. So we have void. So we're going to append destructively, right? We're going to, at the end, none of the original lists will remain in place. So we're going to return a list, but what actually just for safety we return a list, append list, and we have node star L1 star L2, and what do we do? So we're going to have 4 cases, right? One is when both lists are empty, right? So if L1 and L2, then what do we do? You can just return L1, right? So the convention is that none of these lists are okay after we perform this operation. Okay? They're destructive. Everything is mutated. That's where our current convention. Else, if L1 equals 0, right? What do we do now? Return L2. If L2 what do you mean? And now we do all the work, right? The first? I don't understand.
So in the first case, we say that both are empty.
Yes.
And then if you don't have to say by the next statement,
That's true. So if L1.length is 0, then I can just return L2. That's true. All right, else. The question now is, if L2 is 0, then return L1. Okay, that's true. Else. All right, so we're going to use L1 as the result, right? So L1.start is the same, right? And L1 end has to become Y start. the end of L1, L1 becomes the overall list, right? The result. Okay, but before that, L1 and next has to become L2 start, right? All right.
What is L1's
What again?
what is this thing? It's like why the end of L1 is
If I'm going to say return L1, now L1 has the append of the to list, right? Yeah. Why use again? Oh, because I'm returning L1, right? Which is has the same type, right? So L1 has node star, L2 has node star. I'm going to return either L1 or L2 at all times, right? Now, the one thing that I have forgotten to do here is L1 length plus equals L2 length. Okay? And that should be it. Yes? This one should be. Yes, you're true. You're right. Yeah. I did trees yesterday all day, and Node has stuck to me. You're absolutely right. All right. So now you're happy? Everybody's happy? So you would want to do what? To get rid of another one? Oh yeah, so you missed this one. Okay. Happens to the best of us. All right, so we're going to create, let's call this L1. And then we know that this works correctly. And we're going to stop doing this. And then we're going to repeat this for L2. And let's say here I times 10. All right, now let's do a print list of append. Actually, all right, so let's print list L, and then maybe we don't need to remove anymore. So let's see what we have obtained. All right, we have a 0 there. Oh, which is normal, right? Because 0 times 10 is 0, right? So it seems to have worked correctly. So we've created two lists by prepending elements, so they're in reverse order, right? Then we have appended the two lists, and then print it, and it worked correct. That clear? Okay, so let's do another one that is fun, and again, a very typical interview question for software engineering jobs. Let's try to reverse. And actually, we're going to reverse in place. Okay, so the void reverse list of list star L, and then, okay, so if it's an empty list, we don't have to do anything, right? So if L length equals 0, return. Otherwise, so let's have our own pointers to start and end. Okay, so what do? We're going to start, and then we're going to keep 2 pointers, right, for 2 consecutive elements. Right, actually we need 3 pointers on 3 consecutive elements, right? And the middle one has to shift the pointer, the next, from the third to the first, right? That's essentially what happens here. Okay, so in order to have 3 elements, we must have a list with at least 3 elements, meaning that the first case and the second case are special cases, right? So we have no way but to treat these 3 separately. So if L equals 1, right, we're going to do what? Essentially, we reverse the start and sorry, if it's 1, we have to return as well, right? Because there's nothing to do. 1 element reversed is the same thing. So here, obviously, we have to say less than or equal to 1, which is less than 2, right? So as long as length is less than 2, we return. If length is 2, yes. Yes, because we're going to perform an in place. So we're not returning anything. This is void, right? But what we're assuming is that once this has executed, the list has mutated into its reverse. Okay? So if the list L.length is equal to 2, what do we have to do now? So write L start. Okay, let's start with the end. End next is equal to L start, right? L next is equal to null, right? And L and then we're going to have a list star aux equals L start. L, so we have to exchange them, right? Start equals L and L and equals L equals aux. Okay? So let's make sure that we did the right thing, right? So the next of end becomes start, fine. The next of start becomes null because this will become the last element. It's only 2 elements at this point, right? And then I have to exchange the start and end. So I have to use an extra variable. This will support the start. Start then becomes end, and end gets out, right? So it seems to be fine. Else, all right, so we're going to have star p star, and star p equals L star q equals L equals p star p next, and then R star R equals q next. Okay, again, node 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 node. Well, this is the list, the node, right, or the node. So list start gives me a node. So P, Q, R are nodes. Again? Well, they're all pointers. Everything with a star is a pointer. All right? So now we're going to iterate with 3 pointers. Right? So, while, and I'm going to use a while loop here. I could use a for, but I don't want to get overly confused. R next equals null. Right? So, the first thing that we're going to do is say that P next equals null, right? Because this becomes the last element of the list. So then we're going to do Q next equals P, right? Q is the element in the middle. So Q next would be R normally, but I have to reverse it and send the link back to P, right? So now the link between Q and R is destroyed. And now I have to shift the 3 of them. And I'm going to do that with an auxiliary variable. So node star aux, and then this is going to hold P. Sorry, this is going to have also hold R. And then I'm going to have R goes to R next. So R still has a valid next, right? But the other ones don't have valid next. So we're going to have, actually, I don't think I need this. So I'm going to do P equals Q equals R, and R goes to R dot next, right? And then Q dot next is reversed again. And then all the 3 elements go further. Does it make sense? So what happens when we come out of the loop? Right? R dot next is null, and R dot next should not be null, should point to Q. Okay? And now, what we have done is we have reversed all the links inside the chain, meaning that start is pointing to the current end element, and end is pointing to the current first element, right? So we should exchange the elements. And then, because we're doing that no matter what, you can do this here. All right, the length should remain the same. And let's give it a try. So here, in order to test, we should test a long list as well as a list of 2 elements and 1 element, right? So actually 1 element is quite clear that it's going to work fine. But let's first say reverse list of L and do a print list again and see how that works. And aux should not be the auxiliary, should be a node. And we're not lucky at all. All right. So let's see again what's happening here. Okay, so one thing that would be interesting to print would be the P, Q, and R, what they are holding. So we could say %B, %B, %B backslash N, and then we have P data, Q data, and R data. Yeah, so not equal would be a good thing. Infinite list, infinite list. Okay, it went too far. But it's good that we're printing. So while R next not equal to null, so R goes to R dot next. Actually, what I need to do is, well, R not equal null. So if I get to the point where R equals null, then this one should not be necessary. Yes? So P is the first element, right? So this will become the last element. The last element dot arrow next should be null. Right? Q next should become P. right? Which is what we're doing here. So the question is, Q is pointing to, Q is the same as P next, yes, but no longer, right? Because we made P next null. The question is, why is there an infinite loop? Oh no, there isn't. So this is the list. So we have 987, 876, 765. So it seems to be working all right. But then when we try to print, we stop at 0, which means that the last element is not correctly wired. So there's one operation that we're missing here. What is that? We're missing Q next equals P. Okay, success. So now we can remove all the bug messages. And we got the correct result. Okay? Now, this, we are using mutation everywhere, right? And we actually made a big fuss about mutation in Python. We always said it's very bad. Okay? It also so happens to be very efficient. So the tradition in C is, because mutation is very efficient, to provide the first API with mutation, right? And then a very simple thing we could do, which I'm not going to do now, is going to be in your homework, is to copy the list, right? So I could give you a list star copy list L, right? And this is supposed to return a completely fresh copy, not sharing any memory with the old list. Meaning the result returned here and this guy do not share any memory. Okay? Is that clear what this is doing? And then, right, this saves the day. This really saves the day because, right, now let's say I don't want to mutate this, and I want to say a non-mutating reverse. Well, I'm going to take L. I'm going to first make a copy, which is completely fresh, non-sharing, right? And then I'm going to mutate that copy into its reverse. And then the very original list that I started with is still untouched, right? So in this way, we can very easily create non-mutable, so-called pure versions of a function, right? So it's always very easy to do that, right? The problem is that whenever we do that, we incur an extra cost. So in C, we always want to give our client, which is the coder that will use our API, we want to give them the option of using mutation if they so want, right? Because efficiency might be very important, right? And also, it's always a good thing to offer them a function that performs fresh copies of any data structure, right? So then, pure non-mutable versions of any function can be created very easily at the extra cost of performing a copy. Is this clear? Okay, so this will take you a while to figure out why it works, right? It's probably the most complicated thing we've written about lists. Yeah, it's good to try to figure out the algorithm. Next homework is going to be about lists, essentially. Okay, you're going to have to add more operations, like for instance a zip. All right, would be an interesting thing to have, and so on. What I plan to do next is give you a little tour of the library. We haven't touched the library at all, right? I'm always telling you that, oh, is this very rudimentary um, programming language where everything you have to do from scratch, right? Actually, that's not quite true. There are plenty of libraries around. It's always, however, a little bit difficult to install them. Many of them are installed by default on Macs, or if you have Cygwin, they are installed by default. So we're just going to give it a try and try to use them. And then we're going to try to interface C with something, hopefully Python, right? So I'm going to try to show you how to call C functions from Python. So if you were to expand Python as a language, right, how you might be able to do it. We'll see whether that's not too complicated to do for 1.5 hours. But the next two sessions are going to be more around that. Pretty much everything that was algorithmically to introduce about C is there. You are already, you know everything you need to know to solve all the homeworks, right, including the one that is coming. And use the next two sessions to try to go through that, these, and if you have any more questions, to ask them, because we only have 2 more sessions, right? After that, I'm going to be still here for 2 weeks, and then I'm not even in the country anymore. So the only access you will have is by email. So try to take advantage of that. Okay, this is it for tonight. Thanks for coming. See you next time.